Okay, guys, so this is a short video intended to help us review for our Chapter 14 Gas Laws exam coming up this week. This video is not going to solve actual problems, just give you an idea of what the equations that we're using, where we got them from, what they mean. If you need help solving any problems, you can certainly come in to see me, or you could also look back on Edmodo. We've got a lot of worksheets with a lot of solutions up there for each gas law tested. What I'm going to run through here is what are the gas laws, what are their names, what variables were tested, what variables were held constant, what would the graph of the data look like, and what conclusions could be drawn from that graph, i.e. what equations do we end up using in chemistry. Okay, so let's first take a look at Boyle's Law. Boyle, if you remember, found a relationship between pressure, let's keep doing that, pressure and volume. And he finds out that it's a relationship called a direct relationship. And what we want to remind ourselves is what was the demonstration, what was the experiment that we did to do this. And we did a couple things. We put something in a bell jar. We used a balloon. We also used some marshmallows, and we pulled the air out, which reduced the pressure in the bell jar, and we watched the volume of the marshmallows or the balloon change. So Boyle could have done an experiment very similar to this. What he did not change was temperature. No flame or no ice was involved, so only pressure and volume were changing. So Boyle's data might have looked something like this. He would have started out with the marshmallows in the vacuum tube, and he would have recorded pressure and volume as the experiment went on. So if he plotted pressure here and volume on the x-axis, where would he start in this case? Remember, if we start with that vacuum chamber full of air, the pressure is relatively high, and the volume of the marshmallows is relatively small. So this might be our data point right there. And then what happens over time, we start to pull out the air, so the pressure drops, but the volume of the marshmallows gets larger and larger and larger. This is the results of what Boyle would have found in that case. He finds an inverse relationship. As one gets larger, the other gets smaller. So in this case, as the volume gets larger, the pressure on the marshmallow gets smaller. So mathematically, what we see in this case is an inverse relationship. And an inverse relationship in math, a lot of times you learn like this. 1 over x equals y. Really what we could say is some constant over x equals y. And algebraically, what does that mean? It means x times y equals some constant. And that's what Boyle finds. He finds that instead of generic x's and y's, we have P times V equals a constant. So at any time, the pressure times the volume, or the product of the pressure and volume, must be the same. This should be 1 and 1, 2 and 2. Okay, so this is Boyle's Law right here, and this is how we see it written in most of the books or the literature. And that's what it's saying. It's saying the product of pressure times volume is constant. So we can predict one state if we know the conditions of the other state and one of the unknowns. And the 1s and 2s we see in these equations always refer to the states before and after some change. So let's look at our graph up here. Imagine Boyle looks at this as state 1. Pretty high pressure and a small volume, and this is state 2. Low pressure and a high volume. If we compare those numbers, we're going to find out that, well, P1 is much larger than P2, right? This is a lot larger than this right here. But we're also going to find, though, that V2 is greater than V1. Here's V2, and it's greater than here, which would be V1. Again, that's V2. So we see these greater than or less than signs are pointing in opposite directions here, and that's always going to be the case with an inverse relationship. As one gets bigger, the other gets smaller. Okay, next law, Charles's law. Charles investigates the relationship between volume and temperature and holds pressure constant. So did it again. Pressure constant in this case. How is pressure constant in the demonstration in the lab that we did? Well, if we did this experiment, this demonstration where we heated a sealed flask with a balloon, and what's constant about it is the fact that it's always inflating in the atmosphere. So the force of the pressure pushing inward on the balloon is always atmospheric pressure. We don't squeeze in it additionally or anything like that. So the pressure is definitely constant. And what Charles is looking for is as he heats the gas inside here, as he increases the temperature, what happens to the volume of the balloon or the volume of the system. So Charles's law looks at the relationship between volume and temperature, and we would find the data might look something like this. As we continue to heat that flask, we start off at a relatively low volume and a low temperature, right? And as we heat the flask, as the temperature gets hotter, so the volume gets larger. So our data points we would expect during this experiment to maybe look like that. Looks linear. But we have a name for that. That name is a direct relationship. As one increases, so does the other. So a direct relationship is also linear, and we know from beginning algebra class that the equation for a line could be just y equals mx in this case, where m is the slope, and that slope is always a constant value for a line. It doesn't change. So if I do a little bit of algebra, and I'm going to find out then that y divided by x would be the slope, but the significance for us is it's constant. So in Charles's law, with the meaning behind it, y is v and x is t, so we find that v over t, the ratio, is constant. And that's why we see in the literature Charles's law stated this way. So again, let's compare our states 1 and 2. Here we have maybe state 1. I keep doing that. State 1 versus state 2. We heat up the gas and the volume increases, so let's just compare the before and after. If I look at T1 is definitely less than T2, right? This is a higher T than this one. And if I look at V1 versus V2, well, V2 is definitely also larger, here's V2, than V1, right? V2 and V1. So when the greater than or equal signs point in the same direction, that's indicative of a direct or a linear relationship, and we'd always expect that. As one increases, so does the other. Okay, Gala Sack. Gala Sack comes in and holds the volume constant. This would be kind of an example of maybe a pressure cooker, as we can change the temperature and the pressure will change inside, but the size of the pressure cooker itself doesn't change. So Gala Sack holds volume constant and looks at the relationship between pressure and temperature. When he does this, he finds a relationship that should look familiar. As we start off at a low temperature, it's a low pressure. As we increase the temperature inside this pressure cooker, the pressure also gets larger and larger. So we again find that direct relationship. The mathematics is the same as the last slide, but the conclusion would look like this. P1 over T1 equals P2 over T2. The ratio is constant. So again, if we compare the first and second states, we should expect to see that those greater than or less than signs point in the same direction. So let's look here at state 1. A low pressure and a low temperature. So in this case, the temperature and the pressure are both lower than the second temperature and the second pressure. So again, indeed, we do see that direct relationship. Okay, so what if one of those things is not held constant? What if you're heating something up and the pressure and the volume are also changing at the same time? Then we can just combine all those relationships to come up with the aptly named combined gas law. This is what the combined gas law looks like. It's the ratio of P over V divided by T. That will always be constant in this case. This is a good one to memorize because it actually shows you all of the relationships if you can figure it out. What if temperature was held constant, right? That would mean T1 is the same. T1 is the same as T2, so it'd cancel out. You'd be left with Boyles Law in that case. What if pressure was held constant? That would mean P1 doesn't change, so P2 stays the same, and then we're left with a V over T, and that would be Charles's law. And finally, what if the volume doesn't change? If V1 is the same as V2, we're left with the ratio of P over T, and again, that's Gala Sack's law. So we can use the combined gas law when all of the things are changing, but again, if we can remember it, then we actually know all of the other three laws as well. Last law, what I failed to mention in the last demonstrations was that there was also another constant in all of those. The amount of gas was always constant in those cases. So none of Boyles, Charles, or Gala Sack did they, inside of that experiment, change the number of moles of gas. Avogadro comes in and then puts that last piece of information. He does an experiment real similar to what we did in our lab, and figures out that, hey, if we look at the number of moles, which in chemistry we use the variable n, versus the volume, then we find again a direct relationship, and that's what we saw in our lab. We used 3 antacid tablets. It made the balloon 3 times larger than just with 1 antacid tablet. So the relationship is a direct relationship between volume and n. We put that in with what we already know then. We know PV over T is the combined gas law. That needs to be constant. And V is directly related to N, so I can put N there. And that equals a constant. Here's the thing. It's not just going to be any old constant now that we've included N. It's going to always be one constant, R. So R is called the universal gas constant. And I said it'll always be constant, but the value of that constant will depend on how you've actually measured the variables in the experiment. We went over this in class. If we use liters and atmospheres as our units for volume and pressure, this will be R. If we use cubic meters and atmospheres, that will be R. So all of those ones that we would commonly use would be in this table, and you would never have to memorize these. You'd be given a table, but you do have to recognize which one is applicable given a certain situation. Cubic meters and pascals, that's what we're going to use. So I hope this is helpful. Study it, prepare for the exam.